In section 2.6, we're going to look at combinations of functions. The algebra of functions, so let's suppose we start with two functions, f and g. And you can start to kind of think about these as like objects. In mathematics, just kind of like when you are learning like number systems, whether it's whole numbers and then decimals and then fractions, once you kind of get used to those numbers, then the next thing we kind of do is do operations with them, right? You learn how to add, subtract, multiply, and divide whole numbers, then fractions, decimals, etc. We can do the same thing with functions too. Given two functions, we can add, subtract, multiply, and divide them, and what we end up with is a brand new function. For example, we can define the sum of two functions, the sum of f plus g of x, which would be defined using this notation, is simply found by taking the function f of x and adding to it the function g of x. Similarly, the subtraction of two functions, or the difference, the function f minus g of x, is simply obtained by taking f of x minus g of x. We have the product function, which sometimes you can see written a couple different ways. You might literally just see the f and the g kind of written side by side. We know from algebra that that means implied multiplication. The other way that you might see it, and this is very important to visually distinguish, it's more common to see them with a little black dot in between the two, kind of like the dot for multiplication. This also means f times g of x. A little bit later in this section, we'll see a different operation called combination, which has an open circle, but be very careful. When you see that closed dot in between two functions, that means the product function, f times g, is simply obtained by taking f of x times g of x. And then lastly, the quotient function, f divided by g of x, is found by taking f of x divided by g of x. Let's take a look at example 3. They give us two functions, f and g. In A, we were asked to find the function f plus g of x. By definition, this is taking the function f, adding to it the function g. So this is addition of functions. I don't need to put the parentheses here, but I'm going to just for illustrative purposes. We take the expression for f. We're going to add to it the expression for g. And then once we're at this step, we can just kind of combine and simplify like terms. We have an x squared. We have a 2x term and a positive x term that will add to give us 3x. And then the negative 1 and the negative 2 will combine to give us negative 3. So the function f plus g of x is going to be the function x squared plus 3x minus 3. Let's now find the function f minus g. This is by definition f of x minus g of x. And now I will use parentheses again, but this time they're absolutely going to serve a purpose. We're taking the function f of x, and we're subtracting from it the function g of x. This is important because notice that g as a function has multiple terms. Therefore, if you're going to be subtracting g of x, we need to make sure that we're subtracting every single term that's a part of it. To do this, we would first distribute to get rid of this subtraction, get rid of the parenthesis. This would become a negative x squared minus x plus 2. And now that we've done that, we can combine our like terms. We have a negative x squared. The 2x and negative x will make a positive 1x. And then the negative 1 and the positive 2 will combine to give us positive 1. So f minus g of x is equal to negative x squared plus x plus 1. Let's take a look at the next one. In part A, we want to find the product f times g of x. This is simply going to be equal to f of x times g of x. That is, it's going to be 4 over x times 3 over x plus 2. Multiplication of fractions, we know how this works. We can multiply the tops. 4 times 3 is 12. And it's up to you. You can actually leave the denominator in factored form. It's a very common practice. Or if you wanted to, you can expand it out. I think most of us are probably used to doing that at this point. Distributing the x through will give us x squared plus 2x. But this is going to be our product function. F times g is 12 divided by x times x plus 2. For the next one, we want to find f divided by g of x. This is f of x divided by g of x. This is equal to, we're taking the function f, dividing it by the function g. Looks like this. Division of fractions, we know how to write this. This is going to be keep, change, flip. So let me first write it like an old school division problem. This is the division we're trying to do. So I can rewrite it using keep, change, flip. After all, division is the same thing as multiplication by the reciprocal. So we're going to multiply by x plus 2 over 3. This would give us 4 times x plus 2 divided by x times 3, which we write as 3x. Again, if you want to, this is perfectly fine to leave it like this, or you can distribute the 4 into the numerator. So this would be our function f divided by g of x. I'll skip example 5. I'll let you kind of do this one on your own. Again, it's the same thing. Find f plus g, f minus g, f times g, f divided by g. The next one that I do want to look at, this is an important example, is going to kind of discuss the domains of these things. In example 6 part A, we want to find f plus g of x. We know that this is going to be f of x plus g of x. This is going to be equal to the square root of x plus 3 plus the square root of x minus 2. So that's our simplified version. This is the function f plus g of x. The next thing we come to is now the domain of f plus g. And let's just discuss this very thoroughly here. By definition, f plus g of x, this is equal to f of x plus g of x. So going back, what does it mean to have a value of x that's in the domain? Well, what that means is that you're able to plug it into this function, and you're able to get a real number out. Right? That's what the domain of f plus g means. It's what values can I plug into this function so that at the end of the day we get a real number out. If we plug a value into f plus g of x, then according to this formula, that value gets plugged into f, and that value also gets plugged into g. As long as x is in the domain of f, then that means that we'll get a real number out of this piece. And if that same x also happens to be in the domain of g, then we will get a number out of this piece. And at the end of the day, no matter what two real numbers you have, we can take any two real numbers and add them together, which means we'll be able to get an output for f plus g. So what does that mean? To be in the domain of f plus g, the x value we have must simultaneously be in the domain of f, and it must also be in the domain of g, which means it has to be in the intersection of the two domains for the original functions. Okay? This is very, very important. The same logic will also show you that this is also going to be the domain for f minus g and also the domain of f times g. Those three domains are simply found by finding the domain of f, the domain of g, and their intersection, whatever they have in common, that's going to be the domain of these three new composite functions. So let's take a step back. We know how to find the domain of each one of these beginning ones. Let's start with the domain of f. F of x is a square root. So we would need the thing on the inside to be greater than or equal to 0. subtract 3 from both sides, and very simply we get that the domain of f is x greater than or equal to negative 3, which if you wanted to, you could write in set notation as negative 3 to infinity. For the domain of g, it's also a square root, so we need this thing on the inside to be greater than or equal to 0. We add 2 to both sides, and we get that x has to be greater than or equal to 2. So the domain of g is going to be x greater than or equal to 2, which would be from 2 to infinity. Now we're ready to ask the question, what is the domain of f plus g? Again, it should be the intersection of those two sets. So let's graph them side by side to kind of see what they have in common. So here's my number line. And I'm going to graph the first one. Let's do this one in, let's say, green. Greater than or equal to negative 3. If this is negative 3, that would be everything from negative 3 and to the right. I'm going to graph the next one in, let's say, orange. Not orange. Let's do, I don't know. Purple sounds nice. That's too close to blue. Let's go yellow. X greater than or equal to negative 2. So x greater than or equal to positive 2. Well, positive 2 would be here. And that would include everything to the right of 2. So if we're looking, what is the intersection? What values do those two things have in common? The answer is they have everything in common starting from 2 and going all the way to the right. And so that would be the domain of f plus g. It's going to be the set from 2 to infinity. Again, the way that you find the domain of that combination is you must first start by finding the domain of f, the domain of g, and then intersecting the two. And the reason why I say this is, for example, some students will run into a trap where, let's suppose I look at a slightly different example I'm going to make up here. Let me zoom in. Let's suppose, for argument's sake, that I look at the function f of x, which is x plus 1 over x. And suppose that g of x is the function negative 1 over x. If you form f plus g of x, we add those two together, notice that 1 over x and the negative 1 over x would cancel, and so f plus g would reduce to just give us x. And if you just kind of in a vacuum take this out of context and look at the function x, that would be a polynomial, and its domain would be all real numbers. So a lot of students will mistakenly think that the domain of f plus g is all real numbers, when in fact it's not. If we go back up to the original functions f and g, neither one of those were you ever allowed to plug 0 into them. And because the original functions f and g were undefined at 0, so too will the domain of the intersection of the f plus g. Okay, so be very careful when you're finding domains. Don't try to find the function first by the combination and look for the domain then. You need to go back to the domains of the original two functions and find what x values of those two domains have in common. Notice that the one function that I did not write up in this list was f divided by g. And its domain is very similar, but with one extra criteria. So if you wanted the domain of the function f divided by g, let me write it maybe in set builder notation. It's the x's that are also in the intersection of the two. So you have to be in the domain of f, and you also have to be in the domain of g, such that, so this is set builder notation, such that the other thing that you need in order for this to work, not only do you have to be able to get a value out of both f of x and g of x, which is why these values have to be in the domain, But in addition to that, we can't divide by 0. So even if you got 0 out of g of x, that won't work for f divided by g. So it's the x's in the intersection of the two, but with the additional condition that we can't have a 0 in the denominator. The last operation we come to, and this is something that can't be done with real numbers but is unique to functions, is the idea of a composition. Okay, so let's suppose we have two functions f and g. We're going to form the composition of the two, and this is going to be using an open circle notation. We read this as f composed with g of x. Sometimes you'll also hear people say f of g of x, written like this. By definition, what f composed with g of x is you take the function f and you evaluate it at g of x. In terms of kind of like inputs, it's kind of backwards. We read from left to right, but when you're doing function composition, the compositions kind of go from right to left. We put x into g first, you get that value, and then that value gets placed into the function f. Let's get some practice with this. In example 7, suppose we have f of x and g of x, and let's find each of the following. The first one we want to find is f composed with g of x. This is by definition f of g of x. So what I'm going to do is everywhere I see the function f, so my outer function is f, let's copy down the statement form for f. F of x looks like input times 3 minus 4. So my f of x function looks like input times 3 minus 4. But if you look at what we're plugging into that function, we're plugging in g of x, which is x squared plus 6. So everywhere we had an x, an expression for f, we are going to be replacing it with the expression x squared plus 6 like this. And now let's go ahead and work this out. Once we have it plugged in, we can distribute. That'll give us 3x squared plus 18 minus 4, which is equal to 3x squared plus 14. So the function f composed with g of x is equal to 3x squared plus 14. Let's take a look at part B. If we want to do, let's say, g of f of x, this is by definition g of f. So now the innermost function is f of x. To help us get the ball rolling here, let's think about what g does. G is our outer function. The statement form for g, it looks like input squared plus 6. So whatever I'm going to plug into g, I'm going to take that input, I'm going to square it, and I'm going to add 6 to it. Well, what we're plugging into g, the inside part is f of x, which is 3x minus 4. So everywhere we saw an x in the expression for g, we're replacing it with f, which is 3x minus 4. And now that we're here, we want to simplify this. We have a binomial squared. Be very careful. That means to take that thing and multiply it by itself. You'd have to distribute this out. I'm going to skip that work, but you're going to get 9x squared minus 24x plus 16 plus 6. And this would reduce to 9x squared minus 24x plus 22. And that is our g composed with f of x. It's worth noting if you compare the two, and this is why it's very important to pay very close attention anytime you're doing function compositions. If you compare the two in general, f composed with g of x is usually and generally not the same as g composed with f of x. So the order really matters and is very important. Okay. In section 2.7, we will see a very special circumstance when those two will give the same answer. But in general, if you switch the order of composition, you end up getting a different function as a result. Let's take a look at example 8. For part A, we want to find f composed with g of x. This is by definition f of g of x. So the outer function is f. The inner function is g. Let me begin by writing out the statement form for the outer function. F of x is defined as negative 2 times x plus 2. And everywhere I saw an x for the expression for f, we're now going to plug in the equation for g. That is negative 8x plus 12. And then once we have that simplified, let's go and reduce this. If we distribute through, we're going to get a positive 16x minus 24 plus 2, which would reduce to 16x minus 22. So f composed with g of x is equal to 16x minus 22. In part B, if they want us to find f composed with g of negative 3, because we just found that function, we can simply plug it in. This is going to be f composed with g of negative 3. So everywhere we see an x in our function, we can plug in negative 3. This is going to be 16 times negative 3 plus 22. That's going to be equal to negative 48 plus 22, which should be equal to negative 26. Negative 26. An alternative way that we could have done part B, had we not done part A first, is if they asked for this value here, f composed with g of negative 3, this is, after all, by definition, f of g of negative 3. So we could actually begin by finding the value of g of negative 3 first, taking that value and then plugging it into f. If you do g of negative 3, that would have been negative 8 times negative 3 plus 12. That's going to be a positive 24 plus 12, which would be 36. We now take the 36, plug it into f. That's going to give us negative 2 times 36 plus 2, which is negative 72, plus 2, which is negative 70, and that's off. Give me 1 second. Oops, there it is. So sorry about that mistake. When I copied this down, it was a minus 22. I had a minus 22 here. So it should have been negative 48 minus 22. So that really should have been negative 70 here. And that's exactly what we got when we did it the other way. Let's take a look at the next part of this. We now want to find g composed with f of x. Recall that this is, by definition, this is equal to g of f of x. So starting with the outermost function g, remember g of x is the function negative 8x plus 12. So g says to take your input, multiply it by negative 8, and add 12 to it. Like this. And what we're plugging in on the inside is going to be the function f. F of x was negative 2x plus 2. negative 2x plus 2. And now we just have to go ahead and simplify this. If we distribute the negative 8 in, that'll give us a positive 16x minus 16 plus 12, which is equal to 16x minus 4. So g composed with f of x is equal to 16x minus 4. In what should be labeled part D, they want g composed with f of 2. Well, we just found that function. That was the answer to the previous part. G composed with f of 2 will be equal to 16 times 2 minus 4. That is 32 minus 4, which is going to be equal to 28. So g of f of 2 is equal to 28. Let's do another example of this. In example 9, we want to do f composed with g of x for the function square root of x and x minus 6. Again, this is by definition f of g of x. This is equal to, the outer function is f. F says to take the square root of your input. And what we're plugging in is the function g, which is going to be x minus 6. So f composed with g of x is going to be the square root of x minus 6. We can then use that expression to find f composed with g of 7. That's going to be the square root of 7 minus 6, which is the square root of 1, which is equal to 1. We now want to find g of f of x. This is g composed with f of x. So we're starting with the outer function g first. G of x is x minus 6. So g of x looks like input minus 6. And inside of that, we're plugging in f of x, which was the square root function. So g composed with f is going to be the square root of x minus 6. We can use this for part D. G composed with f of 9. This is going to be equal to the square root of 9 minus 6. That's going to be 3 minus 6, which is equal to negative 3. So g composed with f of 9, we get the output negative 3. One last thing before we move on to section 2.7 is let's talk about the domain of a composition of functions. Okay. One of the ways in which you can think about a composition of functions is as a sequence of successive output-input pairs. Okay. One of the analogies, if I wanted to kind of schematically diagram f composed with g of x, okay. If you think of, let's say, suppose f and g is like a function. You think of like x as being your input. F is some kind of rule. Think of it like a machine or a function. A lot of times it's an equation, but it could be a graph, a table, or a chart that tells us how to assign a value to the input of x, and that gives us our output. So our input is x, which is in the domain, and then we get this output from this function, which would be at what we call label f of x. Let's talk for a minute about what is the domain of f composed with g. Again, the domain should be the collection of x values that we're allowed to plug in such that we get an output from this function. F composed with g means we first have to take the x value. Again, remember, function composition, it goes from right to left. So you'd first stick it into the function g, and that output we call that g of x. We then take g of x and plug it into the function f, and what we would get out would be the output, which would be f at g of x. So to get a value out of the composition of functions, we need to be able to complete this entire procedure. The first thing we notice is that in the very beginning, x has to get plugged into g. And what that means is that x must be an element in the domain of g, right? In order for x to be plugged into g, that means that x has to be in the domain of g. Then the next thing that we have to do, once we get that output g of x, that value must be allowed to be plugged into the function f, which means that g of x, that value must be in the domain of f. If g of x is in the domain of f, then we can plug it in, and we will get an output as a result of our composition. So this is the domain of a composite function. It's the x's in the domain of g, such that the g of x value, the output, is in the domain of f. Okay. And this is stated in the notes.